Alright, now we're going to start talking about the motion of a gas. Okay? And when we're really talking about motion, we're talking about the kinetic energy. Okay? Because the velocity, kinetic energy obviously is the energy of motion, and the velocity of a gas molecule is directly dependent on its kinetic energy. Okay? Kinetic energy is also directly related to temperature. Okay? So if you increase the temperature of a gas, you're increasing the kinetic energy of a gas. We know this from our gas laws like Charles's law. And at the same time, you're increasing the velocity of the gases. So just to go through a few of these. Alright. Note the word average. A measure of the average kinetic energy of a gas is the absolute temperature of a gas. Okay, because again, kinetic energy and temperature go hand in hand. But notice an average. When you're dealing with a large sample of gas, okay, gas molecules, they're going to be colliding all over the place. And the collisions against the side of the container are going to be different depending on basically each particular molecule. Okay, the force exhibited and the pressure that we calculate is an average pressure. Okay, and it's because each individual gas molecule has an average kinetic energy. Okay, it's all related to, you know, the collisions and the directionality that it has before it actually contacts the walls or the sides of the container. Right? And obviously, there's more motion with increasing temperature. I don't think I have to spend much time on this. Okay, again, the individual molecules themselves have varying speeds. We're talking about the average. Okay, just a case in point here, we have a molecular speed here for two different samples of nitrogen, or maybe the same nitrogen sample. It's just at two different temperatures. And you can see that the average, okay, the average is higher for the 100-degree sample compared to the 0. But at the same time, there's molecules going at the whole spectrum of velocities on both samples. It's just that the average is higher at the higher temperature. Okay, that should make sense. Effect of a volume increase on constant temperature on average molecular speed. Well, volume increase does nothing. Okay, again, speed would be dictated from kinetic energy. Kinetic energy is dictated by temperature, not volume. So you're going to have more collisions and the pressure will go up. Okay, well, I'm sorry, for increasing volume. You'll have less collisions and the pressure will go down. Okay, but the speed of the molecule should stay the same. That's assuming there's no temperature change. Okay, temperature, on the other hand, is directly related to the speed. Okay, so if you're increasing temperature, speed will go up. Alright, couple words here, effusion and diffusion. Okay, they all have to do with, both terms have to do with gases going from point A to point B. Okay, in a fusion scenario, you're having a tiny hole or a pinhole into some sort of gas container, and it's the rate at which the gas actually comes out of the container. Okay, so you could have that if you put a piece of tape over a balloon. You can put a pinhole in a balloon, have gas leak out. Right, and then you can have do a comparative analysis. If you had two gases in the balloon, you should be able to figure out which one will escape first with the equation that's coming out. Diffusion, on the other hand, is just a race. It's a foot race across space. Okay, an example would be if I had a sealed container of gasoline, a sealed container of perfume in the front of a classroom. I take the lids off both containers at the same time. Um, you should be able to smell one of them with your nose being the indicator, one of them before the other. Okay? And both of those are actually based on the mass. Okay? Heavier molecules go slower, lighter molecules go faster. Okay, RMS means root mean square. It's a velocity term. Okay, and I believe we have our actual formula here. Here's our root mean velocity equaling 3RT over the molar mass, big capital M. Okay, it's a very, very simplistic equation, and it's given to us on the College Board. Rarely comes up as well. Okay, we've already talked about this. Increasing temperature makes the speed go faster. Increasing volume does not. Okay, mixing with another sample. Okay, mixing with another sample of argon. Okay, a noble gas. What does that do? Well, it doesn't do anything. Okay, the velocity of the gas will stay the same. It's just that there's going to be more collisions because there's argon in the way. Okay, so goes up, does nothing, does nothing. Not going to do that calculation. Okay, effusion and diffusion will use this equation, which looks somewhat familiar. It's a comparison. Okay, this is the gasoline versus perfume race. It's all based on molar mass. Okay, how did this, the derivation of this equation is from this equation. Okay, it's just a comparison where you put this over another one. You put one gas over another. Okay, so if you put one gas, I'm going to call this RMS1, RMS2. Okay, which means we're going to have another one of these. This is 1, this is 2. What actually ends up happening is cancel, cancel. You actually end up having M2 over M1 square rooted. Okay, so that is the actual derivation. This equation, it rarely comes up. Okay, they give it to us on the College Board, on the AP test. Rarely comes up. We're just going over it because that's how our Graham's law equation, that's much neater, came about. Okay, so it's a comparison. Note that the diagonal, where did the diagonal come from? We just did it. Okay, that your rate of the one gas when you're doing the molar masses will go on the bottom. And this is usually a fairly fun equation as for solving molar masses or rates of speed. Usually we don't actually give you, okay, usually the rates are not given. You're looking at something like a number here, okay, which would be, if you have a number 4, this means that gas 1 diffuses or effuses 4 times the rate of gas 2. Okay, so the comparative rate over rate will give you a times faster approach, which is kind of nice. Alright, and there we go. Also, note that we have times. Okay, if it's a foot race, you can also have a time going on here. And also note that, again, the 2's and the 2's are switched. Or I'm sorry, the 2's and the 1's are switched. And what I'm saying is, the rate is distance over time. Okay, T1 over T1, D2 over T2. If you're doing a race and you're going from A to B, what I mean by going to A to B is obviously the same distance. Okay, if you're doing a race and the distances are the same, okay, what that means is that D1 and D2 cross out. So you're left with a reciprocal 1 over T1 over 1 over T2, which gives us this. Okay, so that's another neat formula that we made, never have dealt with, rarely comes up, but note that the times, because you're going over it's a race over the same distance, you can also come up with this equation based on time. It'd be up to you to figure that out. Okay, it rarely shows up, if ever, but we should be able to handle that. A couple examples that I don't want to cover. Okay, helium and oxygen, it's a comparative. Okay, you're just comparing the rates, and you're going to find out that putting the molar masses in there, that helium diffuses 2.827 times faster than oxygen. Okay, hydrogen and xenon, same thing. Okay, so you're going to do the same thing based on the mass and get the answer. Okay, in this one, we're going to find the molar mass of a CH gas. Okay, CH means C to the X, H to the Y. X, we don't know the proportions or what the actual formula would be. It's a CX gas, and you're going to do a comparative here based on time. Okay, and solve basically for the molar mass to see if you can figure out what gas that is. Okay, that's a nice problem, and I think we actually do that one here. You do the math on it, and you find out that it's 16 grams. Okay, CH, C to something, H to something. Okay, if it's going to be 16 grams, that means you only have one C, and your only option here at this point is C. Sorry. Your only option here is going to be CH4. Okay, so that's your actual formula. But I know I didn't even read that. You can read through that and handle that on your own. Okay. Mean free path is a term, okay, to show how far a gas has to diffuse before it actually collides with another one. Okay, with another gas molecule. Right? It's nice to know that exists. Okay, there's an average distance traveled between collisions. I've never seen it tested, but it's a nice notion to know. Okay, because if you have a higher density of gas, okay, if you have a higher pressure and a lower volume, this distance will be lower compared to maybe an evacuated tube that only has a few gas molecules, where the distance will be higher. Okay, so there's a mean free path value out there, but we don't have anything to go along with that. And that sums up basically all the types of calculations we can do based on velocities of gases. The key takeaway would be the Graham's law equation. Okay. Also know that the derivation like this with the time based and why you could easily come up with the time based. Also, it's pretty important to know kinetic energy and temperature going hand in hand. Okay, and how kinetic energy, the energy of motion, is related to velocity.